Hi, I'm Dr. Andrew Bernard from Michigan Tech University, and I'm here today at PCB Piezotronics to demonstrate the concept of measuring your system noise floor. So when making a measurement, how do we know that we're measuring the intended sound from our source of interest? Well, first we have to understand something about the amount of background noise in our environment and in our measurement system. So there's several types of background noises we need to worry about. There's environmental acoustic noise, interfering noise sources of other mechanical systems in the room, and the electrical noise floor of your transducers and your data acquisition system. Usually the environmental noise and the interfering noise sources are dominant at low frequencies. At higher frequencies, the electrical noise floor of the transducers and the data acquisition system dictate the overall noise floor of your measurement. In order to make a good measurement, we need to understand the total system noise floor and ensure that our measurement is at least 10 dB above that noise floor as a general rule of thumb. So the equipment we'll be using for the demonstration today is a laptop, compact DAC data acquisition system with a 9234 data card in it, a 50 ohm resistor, a PCB 401 B04 source follower, a PCB 480 E09 signal conditioner, and then two microphones, a half-inch free-field condenser microphone, the PCB model 378 B02, and then a quarter-inch free-field condenser microphone, PCB model 378 CO1. So now we'll demonstrate the system noise floor with several different components. And what you see on the screen is the power spectral density measurement from all the measurements we're going to make. And we'll start out with just an open measurement of the power spectral density of one of these channels. Now, I don't ever recommend taking this measurement because these channels are meant to be terminated with a resistance. But just to give you an idea of what the noise floor looks like when they're open, you can see it on the plot here. If you really want a noise floor measurement of the data acquisition system, you should terminate the connector with a 50 ohm terminator, as you see here. And as you can see by the result, the 50 ohm terminator lowers the noise floor from about 100 hertz up to 10 kilohertz by anywhere from 8 to 15 dB. And we have a nice flat noise floor now. So now we've defined the noise floor of the data acquisition system. The next thing we want to do is define the noise floor of our cables. If we're going to power an ICP transducer, like these microphones over here, we want to actually send that ICP power down the cable when we measure the noise floor of the cable. So at the end of the cable, we need some sort of sink for that ICP power. In this case, we're going to use the PCB 401 B04 source follower. And we have a 50 ohm terminator on the end of that. Now you'll notice on the plot, we're looking at the green curve now. That trace looks almost identical to the terminated data acquisition system at frequencies above 100 hertz. So those frequencies, the cable is not picking up any noise. It may be picking up some noise from 20 hertz to 100 hertz. Next, we can plug our transducer in. What we'll be using here is the 378 B02 half-inch free-field condenser microphone going through our 480 E09 signal conditioner and into our data acquisition system. So the ICP power is being supplied by the signal conditioner in this case. Now we see at frequencies below 10 kilohertz, the entire noise floor is dominated by the acoustic noise that the microphone is picking up. Above 10 kilohertz, from 10 to 20 kilohertz here, you can see that the noise floor is now somewhat contributed by the electronic noise from either the microphone or the data acquisition system. So the next thing we can do is we can bypass the external signal conditioner and we can power the microphone directly from the data acquisition system. And this is often done in industry to cut down on the number of pieces that you use. So when we do this, we see that the noise floor below 1 kilohertz is dominated by the acoustic noise, but then above 1 kilohertz, the noise floor is dominated by the electronic noise. And you may ask yourself, why is this curve 20 dB lower than the last curve, since we're measuring the noise in the same room? Well, the reason is that the signal conditioner was set to times 10 gain. And you can see why that may be important if we want to make measurements in the measurements of the background noise in this room in the 1,000 to 10,000 hertz range, we need to amplify the microphone signal before it gets into the data acquisition system. And that's what you see here between the light blue curve and the black curve. So the last thing we can do is try a different transducer. Here we'll use the 1/4 inch ICP powered microphone. It's a free field condenser microphone, the 378 CO1. Compare that to the 1/2 inch. Now the 1/4 inch microphone has a lower sensitivity, which means it's going to have a higher noise floor. And when we make that measurement, you'll see that the system electronic noise dominates the measurement above a kilohertz. And below 1 kilohertz, we're dominated by the acoustic noise in the room. So the takeaway from this video is that it's very important to measure your system noise floor from your transducer through your cables to your signal conditioner and into your data acquisition system, and understand each of the components before you go and take a real measurement. I hope you found this video informative, and I hope to see you next time.
For more information, visit pcb.com or give us a call at 1-800-828-8840.